In the next few videotapes, we will be studying trigonometry. This tape, which is the first in our sequence on trigonometry, is entitled Angles, Degrees, and Radians. It deals with a discussion of angles and how we measure them. An angle of any size can be generated by a ray or a half line, which is rotated about a fixed point, which is called the vertex, from an initial side to a terminal side. A ray or a half line is something like this. You know, a line extends indefinitely in two directions. The ray or the half line starts at a fixed point and goes off in only one direction. Okay, here is the initial side, and this is the terminal side. Okay, and as I mentioned, the angle is generated by a ray or half line, which is rotated about a fixed point or vertex from an initial side to a terminal side. In this particular example, we rotated in the counterclockwise rotation. If an angle is generated by a counterclockwise rotation, we call it a positive angle. If the angle is generated by a counterclockwise rotation, CCW for counterclockwise rotation. The clock goes this way, this is counterclockwise. If the angle is generated by a counterclockwise rotation, we call it a positive angle. Okay, we could also start like so, vertex, initial side, and generate the angle by a clockwise rotation. The initial side, this would be the terminal side. An angle generated by such a clockwise rotation is called a negative angle. Clockwise rotation, we would have a negative angle. The angle is generated by a clockwise rotation. We call it a negative angle. Let's look at the coordinate axes, the x and the y axis. We can position our angle so that it is in what we call standard position. An angle is in standard position if its vertex is at the origin and it has the positive x-axis, this portion here, as its initial side. So, for example, an angle like this is an angle in standard position. Okay? We could indicate this angle. We could give it a letter name. We could say this is, say, the angle theta. Or we could represent it by, very commonly, by three letters. Angle AOB. Okay? We write down the definition of standard position. An angle is in standard position if its vertex is at the origin. Okay, that's the point of intersection of the x and y axes. If its vertex is at the origin and it has the positive x-axis as its initial side. We will speak of an angle being in a quadrant. quadrant 1, 2, 3, or 4, if the terminal side of that angle, when the angle is in standard position, if the terminal side of that angle is in that quadrant. So, for example, here, angle AOB is a second quadrant angle because its terminal side, when it's in standard position, its terminal side is in the second quadrant. You'll remember this is quadrant 1, 2, 3, and 4. The quadrant that an angle is in is the quadrant that contains its terminal side when the angle is in standard position. So in the diagram over here, angle AOB is a second quadrant angle. It is in the second quadrant since its terminal side is in the second quadrant. We might also say that it is a positive angle since it has been generated by a counterclockwise rotation. So in this picture, angle AOB, and this symbol can represent an angle, angle AOB is a positive angle in the second quadrant. We are interested in measuring the magnitude of an angle, measuring its size. We have two ways of measuring the size of an angle. One is to use degrees and the other is to use radians. Degree measure is the one that you're probably already familiar with. Degree measure. These are ways of measuring the size of an angle. Okay, this is based on the idea that dividing the circle into 360 equal parts and considering a complete revolution, okay, a complete revolution to be a rotation through 360 degrees. We divide the circle into 360 equal parts, and one complete revolution is a rotation through 360 degrees. In this way, we measure sizes of various angles. For example, the measure of an angle would be 1 degree if the angle was generated by 1/360th of a complete revolution. Or we could say the measure of an angle is 90 degrees. Okay, if the angle is generated by 90/360ths, or 1/4 of a complete revolution. This little circle here is the symbol for degree. Okay, the measure of an angle is 90 degrees if the angle is generated by 90/360ths, or 1/4 of a complete revolution. So, for example, a 90-degree angle would look something like this. The initial side and the terminal side. This is 1/4 of a complete revolution. Okay, another 90 to bring us here, another 90, 360 to go all the way around. A 90-degree angle, of course, is also known as a right angle. The initial side and the terminal side are perpendicular to each other. Okay, and as I said, this you are probably already familiar with. We can use a protractor to measure the size of these angles. You would lay it off here, and you would look to see, in other words, where the terminal side is, and that would tell you the size of the angle. This you're probably familiar with. Now, most of you are going to go on and, well, not most of you, well, some of you, let's put it that way, are going to go on and study calculus. It turns out in calculus, for reasons that will be explained in the calculus classes, in calculus we have to measure angles in a different way. We have to use radian measure to measure angles. Now, since you're most familiar with degrees, you'll probably always continue to think in terms of degrees. That's perfectly all right, as long as you understand radian measure and able to go back and forth between degree measure and radian measure for an angle. Okay, by the way, this business of saying the measure of an angle is 90 degrees, okay, it's a little formal. If I talk about a 90-degree angle, I'll mean an angle whose measure is 90 degrees. Okay, so we don't, if I leave out the term measure, talk about a 90-degree angle, okay, you'll know what I'm talking about. As I mentioned, the other way of measuring an angle is to use radians. Okay, the angle is the same. The principle of measuring it is a little different. Let's say we have an angle theta. Here's the initial side. Here's the terminal side. This is the angle theta. Okay, we're interested in the radian measure of this angle. What we do is we draw a circle, okay, that has as its center the vertex of this angle and has some radius, let's say r. Let's say, okay, that's the radius of the circle. It doesn't matter, you'll see why in a moment, what the size of the circle is. Okay. We take this angle and we think of it, in other words, as a central angle of some circle with radius r. A central angle is one whose vertex is at the center of the circle, okay, and has radii of the circle for the initial and terminal sides. Okay, now if you look at this angle, you will see that it cuts off a certain segment of the circle here. It cuts off a portion of the circle. This is called an arc of the circle, the segment of the circle from here to here. Okay, let's measure the length of this. Let's say that the length of this intercepted arc is s. Then the radian measure of an angle, okay, theta in radians, is equal to the length of the intercepted arc divided by the length of the radius of the circle. Now we'll assume here that s and r are given in the same units of length. S and r are given in the same units of length. Okay, so theta is a pure number. In other words, s could be a certain number of inches and r is a certain number of inches, and when you divide, the unit cancels out. The radian measure of an angle will come out to be a pure number. Now you can think of it as such and such many radians, okay, but it's not really a unit in the sense of inches or feet or something, because it's really a pure number. If it makes it feel better, we can use the term radians. Okay, but basically, it's the length of the intercepted arc divided by the length of the radius. Now, you may say, well, doesn't it make a difference what size circle you put around this? Actually, it doesn't. Let's say we had used a much smaller circle. We still have the same angle, but we had drawn a circle looking something like this. You will notice that s is smaller. In this case, the intercepted arc. R is also smaller. But it turns out that the quotient, S over R, is the same, and that's what's important. The radian measure of the angle does not change. It is not affected by the size of the circle. A bigger circle, S will be bigger, R will be bigger, but the quotient turns out to be the same. So the radian measure of the angle has nothing to do with the size of the circle that you put around it. Okay? It is just a function of the angle itself. It's dependent only on the angle itself. Now, as I mentioned, most of you are familiar with degree measure, and radian measure is rather new to you. It is important that we have some way of going back and forth between the two types of measure of an angle. And we will be able to develop some sort of a conversion, okay, that we can use, some conversion factor that we can use to go between these two types of measure. To do this, let's consider an angle of 180 degrees, also known as a straight angle. Okay, we have an angle. Here's the initial side. 90-degree angle, we know, looks like that. 180-degree angle would be generated by 180 over 360, or 1/2 of a complete revolution. Okay, and it would look like a straight angle, straight line rather. The initial side and the terminal side, okay, would extend, and it would just look like it's just part of a straight line. 180-degree angle. let us now get the radian measure of this angle. We'll use that as a conversion factor between the two types of measure. To do that, we will, draw a circle whose center is the vertex of this angle, and let's say it has radius r. Okay. We've considered this angle, theta, say, to be a central angle of this circle that has radius r. Now, if you remember back from geometry, the circumference of a circle of radius r is 2 pi r. That is, the distance all the way around the circle is 2 pi r. In order to get the radian measure for this angle, I would need to know, of course, the length of the intercepted arc. Okay, now if the whole way around the circle, that's the circumference of the circle, is 2 pi r, then then the length of this intercepted arc is 1/2 of the circumference, 1/2 of 2 pi r, or just pi r, where r is the radius of the circle. Let's go over that. To get the radian measure of the angle, we know the radius of the circle. We need to know also the length of the intercepted arc. This is the initial side, and this was the terminal side. Okay, this is the intercepted arc. Notice that is 1/2 the entire circumference of the circle, but the circumference of a circle is 2 pi r. 1/2 of 2 pi r is just pi r. The radian measure for this angle, theta, is, of course, s over r. But s is pi r. That is the intercepted arc, the length of the intercepted arc, and r is the radius. So we see we have pi r over r, or just pi. Pi is the radian measure of this angle, theta. Its degree measure was 180. Its radian measure is pi. So we could say, and by the way, you could say that it's pi radians, if that makes you feel better, if you want to give it a unit. It's perfectly okay, just say the measure of this angle is pi, or the radian measure of this angle is pi. Okay? Here we have an angle whose measure is 180 degrees. We see its radian measure is pi. In other words, an angle of 180 degrees is equivalent to an angle of pi radians. An angle whose measure is 180 degrees is equivalent to an angle, or equal to an angle whose measure is pi radians. And we're going to use this to be able to convert between the two types of measure. Everybody see this? 180 degrees, a straight angle, the length of the intercepted arc over the length of the radius, pi r over r, the r's canceled, pi radians is equivalent to 180 degrees. Okay, now to use this, to enable us to go between degree measure and radian measure, I just want to remind you how you would convert, say, between other units that you might be more familiar with. And we're going to use the same idea here. Okay, you are aware of the fact that 12 inches is equal to 1 foot. You've used this to convert. I mean, you may not have done it formally, but you are able to convert between inches and feet without any difficulty. For example, if you have 3 feet and you want to know how many inches, okay, let's do it very rigorously here, okay? And this, by the way, this idea would also help you in some of your science classes. The conversion might be something more complicated than inches to feet, something between grams and pounds or what have you. You could work it the same way. To go from feet to inches, in this case 3 feet to inches, we multiply by 1. It's always okay to multiply by 1, and we multiply by 1 in the form 12 inches is equal to 1 foot. In other words, since 12 inches is equal to 1 foot, we have multiplied by 1. We choose to multiply it by 1 in this way so that the feet cancel out. 3 times 12 gives me 36 inches. So to go from feet to inches, you multiply by 12. Okay, and the reason is that 12 inches is equal to 1 foot. The feet will cancel out. The unit will remain inches, which is what you want. On the other hand, let's say you had 24 inches and you wanted to convert to feet. You would multiply by 1 using the reciprocal of this conversion factor. You would say 1 foot is equal to 12 inches, so I'm multiplying by 1. But now the inches cancel out. 24 over 12 feet, or 2 feet.